This conference will now be recorded.
All right, I think we're on. Greg, can you confirm that you can hear us in the... You're good? Cool. Hey, everyone. Thanks for your patience. My name is David Apperson. I'm a licensed professional engineer. I'm also an HVAC mechanic. I work for Cool Air Mechanical, and I'm currently making my way through an apprenticeship with the local plumbers and pipe fitters local 367 union. This is a pretty cool photo. All the photos in this slideshow I personally took. This photo was on a charter flight that I took to the village of Nikolai for some HVAC service over there a couple of years ago. This is the Kachatna Cathedral Mountains in the Alaska Range. Really, really beautiful. So here's a little bit about me. I grew up in Seward, Alaska. My father was an HVAC mechanic, and my entire life he encouraged me to study engineering. And when I became an engineer, he was insistent that I do everything I could to be the type of engineer who was always thinking about the person in the field. In 2012, I graduated with my bachelor's in mechanical engineering from UAF. Had a fantastic time up there. I then worked at Siemens Building Technologies doing HVAC controls. My role at Siemens was a combination role. I was a project manager, a controls designer for HVAC systems, and then also a field technician. I then worked for PDC Engineers as a mechanical EIT. I did heating and cooling load calcs and drafting and all of the other duties as assigned. I really enjoyed my job there. It was a fantastic place to work. Eventually, I started to realize that if I wanted to be the best engineer I could possibly be, I needed to have a tighter feedback loop for my understanding. It seemed like the types of decisions I was making, it was taking a really long time for that feedback of those poor decisions to get back to me, like many years. And it seemed like a good way for me to learn would be for me to work in the trades where the feedback loop is like immediate. Like if you break something or if you fail, like you find out firsthand directly. So I made a really difficult decision to leave the engineering job that I've worked my entire adult life to get. And then I went back to my hometown of Seward, and I studied at AppTech and took their plumbing and heating program. And there was a lot of humble pie in learning and realizing all the things that I didn't understand. And that was just like basic plumbing and heating stuff. Then as soon as I graduated from that one semester program, I then joined the local plumbers union here in Anchorage and began working as an apprentice HVAC mechanic with Cool Air Mechanical. So why should you listen to me? That is a good question. So a huge lesson that I've learned while working in the trades is that everyone has something to share. Everyone has something to contribute. Everyone has their own form of a genius, and everyone can be really stupid sometimes and make some really bad decisions. So it's important to just stay quiet and listen. At least that was my personal perspective of listening to a lot of journeymen that I was working with. Here's an interesting quote from Ralph Waldo Emerson. In the minds of geniuses, we find once more our own neglected thoughts. So here's a brief overview. We're going to talk about what I jokingly call the wheel of ignorance. We're going to talk about some of the lessons learned, my personal lessons learned since being in the trades, the engineering versus trades perspective. Throughout this entire presentation, we're going to have a theme of ongoing themes that everything breaks, entropy does not stop. We need to continue to think about the interface and exchange of all the fluids that we're designing around. Redundancy is critical, especially for commercial and industrial systems. We also need to be continuously thinking about maintenance access because everything breaks. So if everything breaks, who's going to show up and fix it? How will they get their hands on it? We'll talk a little bit about equipment specifics for plumbing, heating, ventilation, air conditioning, refrigeration, and mechanical room layout. And then at the end, inspired by my friend Glenn Evans, we're going to talk about some self-care lessons learned This photo is at a coal-fired power plant in interior Alaska. That is a 12 million BTU oil-fired boiler. And that was one of the happiest moments of my professional career, was making that boiler work right. We had worked, me and another apprentice tag team, that boiler and another one. We'd worked 14-10 straight, and it was rigorous, and I was super happy to be done. So let's talk briefly about the Wheel of Ignorance. So everyone on this wheel seems to think that they know better than everybody else. The plumbers think that they're smarter than electricians. Electricians know they're smarter than the plumbers. The HVAC mechanics think they know more than the electricians and the plumbers. The engineers and architects think that they know more than everybody else. The project managers think that they know more than everybody else. The owners, you get the idea, like around the wheel. So it seems like whenever we look around this Wheel of Ignorance to the people who have a different perspective, like we have no idea what they're thinking, but we need to have humility to recognize that, oh, well, maybe they know more than what I think they know, and maybe I know a little bit less than what I think I know. And this has been my personal experience, at least. So it has been honestly really kind of brutal for me, stepping from a white collar engineering perspective into a blue collar mechanical trades perspective. Because really nobody cares. And so you just got to work your ass off and kind of prove that you're not an idiot. Some similarities though, because it's a Venn diagram, it's not like there's these two separate worldviews. But something that I recognized immediately once I began working as an HVAC mechanic was that the journeyman perspective, like once you've gotten to a certain level of proficiency and competency, the journeyman perspective is, I am going to figure this out. And that is analogous to the professional engineer perspective of, I am going to figure this out. So when I was working as an AIT, I didn't know much of anything, and it always seemed like I was constantly having to go back to the professional engineer that I was working under. And then as soon as I started working as a apprentice HVAC mechanic, I also didn't know anything, and so I continued to have to go back to journeyman. But the EIT and professional engineer relationship is remarkably similar to the apprentice and journeyman relationship. There's like a mentorship and a back and forth. How do you learn from somebody else? And as soon as I realized that, these two types of perspectives are the same, that we have to choose that I'm going to be the person who figures this out. That's when I really started to make a lot of progress, both in my professional engineering experience and then also as my current experience as an HVAC mechanic. So it has been really different. The white collar perspective is, you got to keep yourself and keep your work area organized and tidy. We talk a lot about the way the world should be. It's cautious, specific, precise. Your ideas are important, and we discuss ideas using the Socratic method. Clear and deliberate thinking is valued, and communication is usually pretty clear. In the trades, that is not really the case. It's a blue collar perspective of get in there, get messy, you can clean it up later, just get it done. Things are a little bit loose, as long as you kind of make it work at the end, that's all right. You're allowed to be really rough with things. You just got to just fix it. Your ideas are definitely not special. And the physical output is the thing that's valued. And communication is often assumed and not clear. But anyway, let's just move on. So the culture, work hard, be nice, keep your mouth shut. Because nobody really cares, what you think. They care more about, can you solve the problem? Every plan you ever create will fail. That's not different in the trades versus in the engineering world. But what's more important is, when that plan inevitably fails, how are you going to respond to that? As I got better and more proficient working as an HVAC mechanic and technician, and I was able to solve more complex problems, I realized that, nobody ever wanted to hear what my excuses were. So no excuses, just play like a champion. Show up and just choose that you're going to solve the problem no matter what. And I can't tell you how many dozens of times I've been in a dark, dirty, loud mechanical room, really stuck, not making progress on a problem. wanting to quit and go home and be like, man, this is stupid. Like, what am I doing with my life? And then 5 minutes later, realizing like, well, nobody's going to show up and help me with this. So I have to just stick it out and just struggle until I succeed and find a way or make a way. So the ongoing themes, everything breaks. We're going to repeat these themes throughout this presentation. Everything breaks. Everything breaks. Entropy never stops. Things will continue to rust and corrode and decay on evenings and weekends and holidays. We need to continually be thinking about what is the specific, detailed interface between fluids and the piping or the heat exchangers that we're designing and using. Redundancy. If you have one of something, eventually you will have none of something. If you have one flashlight, you will suddenly have no flashlight. And if you have two boilers, one day you will have one boiler. If you have a single boiler, you are guaranteed to have no boilers on Christmas Eve or our New Year's Eve. And then maintenance access. So a lot of things just kind of get shoved into corners of mechanical rooms because, you know, they sort of fit there on the plans and we don't have a good spot to put it otherwise. And I can get to that stuff because I'm a young, you know, physically fit and really motivated person. But a helpful tool to think about things as we're designing is, could your grandfather access it? Because most maintenance guys are not in their 30s and they don't fit into spots. So here's another interesting thing that's kind of helped me out is how can I think about the work that I'm doing, or how can I think about the building that I'm trying to keep healthy as a biological organism. So the structural steel is kind of like the bones. So the wall and roof are like the analogous to the skin and the membrane of a biological organism. The boiler is like the stomach because is the thing that's creating heat. The heart is analogous to the pumps in the building. You get it. So this is just something that I think about a lot, and kind of what brought it up was if I shut down an air handler to service it, like what am I doing to this? What am I doing to this building? Like that's analogous to stopping this biological organism from breathing. So I need to be cognizant of that. Oh, and then also as kind of like a joke to myself, the HVAC mechanics are like the white blood cells in the immune system, just, you know, scurrying about trying to fix things. Okay, design phase considerations. Man, just keep it simple. High performance usually means high maintenance, and sometimes that's available. But in rural Alaska, that high maintenance is usually not an option. An important question to ask ourselves: is this design robust, or is this design high efficient and sexy? But really, simple is what's really sexy. Everything's going to break, so if something is simpler and more robust, it is less likely to break. Or when it does break, do we have redundancy to back it up? So this photo is of the combustion blower on a high efficiency boiler. High efficiency condensing boilers are great, and you know you can save a lot of money by operating in the condensing range. But that blower costs $700. So and they fail. They fail every 4 or 5 years. Sometimes they will last 10 or 12 years. But, you know, like these are the types of questions we can ask ourselves. Well, okay, if that particular part is a design failure point and it costs $700 to replace, how much energy savings are we getting by operating in the condensing range versus having a cast iron boiler that has a non-condensing burner, non-condensing heat exchanger that you set up once and it runs for 20 years and the HVAC mechanics never have to touch it. Redundancy, the ongoing theme. It is commercial and industrial gear is hard to get, especially now because of the delays of manufacturing due to COVID. In general, commercial gear, if we're lucky, it's going to be that pump or that burner or that blower motor will be in Anchorage. Usually we can get things from the West Coast. Next day air in Alaska usually means 2 or 3 days from now. If it's in rural Alaska and you get something shipped up next day air, that's 4 or 5 days. Industrial gear, this is another reason why we constantly have to have design redundancy in our systems. Industrial gear is usually a custom machine thing or a custom built whatever from the factory, and it's usually weeks or months of a lead time. So the question to ask ourselves and our customers is, what are the redundancy needs? Can we get away with 2 pieces of equipment that are sized to cover 50% of design load? Can we have 2 pieces of equipment sized at 60% of design load? Or does the customer have enough money that they can have 3 pieces of equipment that are sized at 100% design load? So these are the types of questions we need to ask ourselves and our customers. How can we be a better engineer? For goodness sakes, perform a site visit. Oh my gosh, just go to the site. If it's in town, go there. If it's in rural Alaska, you need to go there in the springtime to see what it's like when everything's melting. You need to go there in the summertime to see how hot and dry it's going to be. You for sure need to go there in the wintertime to see how cold and windy it's going to be, because all of those weather conditions are just remarkably different, especially in rural Alaska. Another really important question that I don't remember thinking much about at all when I was working in the office was, how much does it weigh? Because somebody has to move it in the physical world. And yeah, it's really easy to move things around in Revit, and like I just plop it into the building, piece of cake. Well, one time I specified a boiler that wouldn't fit through the door. That was a really embarrassing mistake. Oops. And that boiler weighed, 10,000 pounds or something. Another really easy thing to do to avoid a lot of costly mistakes is just talk to the maintenance guys. They know so much. They're the boots on the ground. They're the ones fixing it. They're the ones who are living with the types of mistakes that we as designers make, and they live with it for their entire careers. So they feel it on a day-to-day basis. Again, how will the equipment physically get into the building when it's being built? How will it get on the roof? There's no magical cranes. A sky crane helicopter is not really an option. Is some person going to haul it up with a rope along the side of the building? Can the floor or the roof support the equipment? Can the floor or roof support the equipment as you're dragging it along the roof to get it to its final location? Yeah, maybe that roof has been structurally and seismically designed to support that equipment in its final resting spot, but on its journey along the roof membrane, maybe you might accidentally broke something on its way to get there. And again, can your grandpa access it? And a helpful cue to ourselves to think about this is, if we had a weight column on our mechanical equipment schedules, that would be super helpful to everybody. That'd be helpful to us as designers. That would be helpful to the contractors, because they're not having to sift through their submittals to see how much does this thing weigh. Does it weigh 1,000 pounds? Does it weigh 5,000 pounds? Okay, things to stop doing. The MBH unit, I think that is really stupid. Nobody knows what that means other than the engineers. So it's also a weird unit, because 1,000 of something in every other context has the prefix of K for 1,000, but MBH doesn't. None of the plumbers know what the MBH means. So why do we even use that as a unit? That's just poor communication, I think. Please stop installing ceiling cabinet unit heaters. They don't work. They don't push hot air down to the floor, and they are a pain in the butt to work on. Galvanized steel pipe is a kind of a crappy material. Basically, the galvanized coating on the inside of the pipe is just the first thing to corrode, and then over its lifetime, it just completely plugs up and gets more and more rusty. The polybutylene gray PEX, it looks like gray PEX piping. That stuff leaks like it didn't even connect it to anything, and so we just need to stop using that stuff. Let's move on. So let's do more of this. Let's locate air vents at the upturn of a piping. So in this photo, I'm pointing at an air vent that is physically connected right at the downturn elbow of piping. And even though it's an auto air vent and it's supposed to have a float in it, it does have a float in it. If they're located at the downturn of piping, they are going to suck in air, and that pipe is going to get airlocked. And then that's another, multi-$100 service call for an HVAC mechanic to show up and just bleed some air out. So if we locate auto air vents on the supply side or the upturn side of piping, we're just going to eliminate that and actually push air out of the system. More strainers and filters are really helpful. In our physical bodies, our kidneys are constantly filtering our blood, and our blood is constantly being pH balanced, but we're not really doing that in our mechanical systems. So, but we could, and that is really helpful. What else we got here? Oh, we got to think about how do we protect the gas regulator from freezing up a natural gas-fired equipment. That is a super common service call, and all we got to do is just physically locate the gas regulator just a couple feet away from anything that has potential moisture, including the exhaust of that gas burning equipment. Okay, how are we doing on time? That is inside of a galvanized steel pipe. That is what every single galvanized steel pipe looks like when I cut into it. It's restricted flow, and that's domestic water pipe. Dude, I don't want to drink that water. That is gross. So let's just stop using galvanized pipe for anything, really. Isolation valves are great. Just put isolation valves everywhere. I mean, because I can't tell you how many times we had to shut down an entire building and drain down the entire building on a multi-floor structure because there just weren't any isolation valves anywhere. And it's like, wow, we just spent 6 hours with 3 people, billing out at $140 an hour to drain down this building, and to install an isolation valve would have cost an hour of time and $100. Holy cow! Let's just get more isolation valves everywhere. At least get them so that on the mains we can shut down, a quarter or a third of the building if we need to do a drain down, or install isolation valves so we can isolate an entire bathroom or toilet battery. Just more isolation valves. They're so affordable, and there's really not a good reason to not install them. Every isolation valve needs to have a low point drain because we isolated that energy, or we isolated that fluid. But if we can't relieve that pressure, then what are we doing? Some jerk has to drill a hole in the pipe and get splashed in the face. Outdoor accessible lift stations. We got a good photo here of making 200 feet of rubber suction pipe through a building because there was no direct access to the outdoors to a basement lift station. That was gross. I like to whitewater paddle, and it's forced me to think about how does water really actually want to flow and move in its natural environment. And so every river wants to flow in a similar way as reverse return piping. So every time the main flow in a river has a channel change, the bulk flow will shift from the left side of the river to the right side of the river. And as it's switching, it will trickle through a bunch of pebbles. Those pebbles are analogous to the terminal units in our hydronic heating piping system. And so a river flows the same way that a reverse return piping system would that we install in our buildings. So that's a pretty good way to pipe things, in my opinion. It's a really good idea to locate trap primers in the men's restroom because men are the ones who are actually, no offense to women, but there's a lot more dudes who are plumbers than women. This is a photo of these rubber compression sleeves that are often used in walls or in underground foundations to prevent leaking for pipes that are going from the basement to the soil. They really don't work. I don't have a super good solution, but they just don't really work. So we got to figure out something else or use a different product. For residential work, or for rural Alaska work, prefab skids of heating equipment, toilet batteries, whatever. Prefab something in town is significantly more affordable than trying to manufacture something in rural Alaska. All right, let's keep moving. Okay, let's look at some photos. This is a photo of a very large chiller at one of our local hospitals. One of my first jobs at Cool Air Mechanical was to take this threaded brush and push it through every single one of those holes. And it took 3 weeks, and I just listened to a bunch of audiobooks. And that was kind of one of the ways that I earned my place as not an idiot at Cool Air Mechanical. This is a humongous heat exchanger, plate and frame heat exchanger. It was all scuzzed up because the strainers on the well water side failed, and so a ton of soil and debris fouled up the well water side. The glycol side was not nearly as dirty. So this is just a picture of a ton of sand and silt that completely plugged up the well water side. And it took 3 weeks to clean out this heat exchanger. And that is a picture of not even half of all of the soil that we washed out of that thing. Check this out. So here's some maintenance access at the underneath of this heat exchanger. We got a little bathtub that trapped all of that silt and soil as we washed it all out. That was really cool. That was a great idea. Whoever put that in their drawings did a really good job. Galvanized pipe, some really poorly installed waste piping. Boy, that was great. Oh, this is a Shellco glycol filter. This is a filter housing. You can pipe this to a unit heater or really kind of anywhere, and it's just like the kidneys in our bodies. It's just a cotton filter that gets replaced as often as you want. They're super great. Highly recommend them. Here's a really poorly installed gas meter. We got to detail this stuff a little bit better. This thing's just floating on some rocks. The piping's not supported. I mean, yeah, like shame on the plumber for doing this, but also we can do a better job as designers of detailing these sorts of things. Lots of leaky glycol things. Boy, it would have been really nice to have, a $3 quarter-inch threaded ball isolation valve to replace that auto event. This is a condensate trap on a condensing boiler. This is a cast aluminum condensate trap. Cast aluminum is not a very good material. If there's any way that we can move away from cast aluminum in relation to kind of anything in hydronic piping, that would be great, because it is the first material that's going to corrode. And I've replaced a whole bunch of these condensate traps. Well, maybe that's kind of nice. Maybe that's like cheap money for me. I don't know. These poly tanks are awesome. There's a couple different manufacturers. This poly tank is really cool and handy because it has two systems that it's serving, so it takes up less floor space in the mechanical room. We talked about that already. Oh, that's a pretty cool stalagmite of glycol. It's just kind of beautiful how that happens. Okay, here's a picture of that Shellco glycol filter. The right-hand side, the bright white one, is the new one. The left-hand side, that is black as sin, that's the dirty one. And that's just stuff that's floating around in the piping that we can trap and collect and clean out our system. If we didn't trap it and collect it here at this filter, it is for sure going to collect in heating coils and VAV boxes or in zone valves and plug those things up, or we could just totally do away with that by having a pretty affordable filter housing. Here's some really crappy gray polybutylene piping that continues to leak no matter how many times I fix it. Oh, another one of those condensate neutralizers or condensate traps. Let's see what else we got here. I'm gonna make some more progress. Oh yeah, lift stations. Yes. Here's a lift station, and there's a little confined space tripod so that I can get lowered down with a cable into the lift station. It's outdoor access. It is relatively sanitary because, the poop just goes on the grass when, you're crawling out of there. There's the pump that we pulled out. This was a pretty good job to do because we didn't really have to worry about making a horrible mess because we're outside. This lift station is a different story. This is what it looks like. That is a cluster of wiring that was really quite challenging to figure out. It would have been nice if that cluster of wiring was not inside the pit. That would have taken a little bit less mental strain off of me to be hovering inches above a cesspool of poop trying to do electrical troubleshooting. Look at that photo, man, that's beautiful. I don't know if you can see the slightly brownish stain shooting out of that poop pipe, but let's see if we can get a different picture of that job. So that lift station, or this particular lift station that we're looking at, it is in the basement floor of a 5-story building and there is no direct outdoor access to get to this lift station. So let's just look at how much hose we had to haul through this truck. It was a couple hundred feet. So we see this entire hallway that we had to drag hose through. Here's another big long hallway. Here's another one. We're still going. And finally, we had to haul it through a parking garage to get to the septic truck. That is dumb. Boy, that would have been really nice if we had just a door and a short set of stairs to get to that lift station room. But no, I drug a sewage hose through the sterilization area where they sterilize all these dental instruments. And oh boy, what a terrible idea that whole thing was. Oh, another one of these things failed. Boy, you get the idea. Oh, this was a frozen water meter in a parking garage. Somebody accidentally left the basement door open to this parking garage, and it froze this water meter. This water meter assembly, it only gets used once a year to wash out the parking garage. And so we got a strainer, water meter, backflow prevention device, pressure reducing valve. Well, that's a bunch of expensive stuff to get used once a year ever, and then it froze and cost many thousands of dollars to repair. And if you see in this photo on the bottom left, there's a little green baggie. That little green baggie was filled with human poop, and you can guess who got to clean that up. It was me. And so I'm thinking in my head, why did this thing ever have to get built? It would have been so much simpler and more cost effective to have a 1.5-inch pipe coming from the occupied and heated building that's 20 feet away. So that's it. You know, these are the types of things we've got to think about ourselves. When is this going to get used? When it freezes, how's it going to get repaired? So what I did to fix this was installed some electrical heat trace on all of this copper piping and insulated the heck out of it and put a thermostat on there so that it, I really hope it doesn't freeze. Okay, oh, here's a good picture of protecting the gas regulator from the water vapor coming out of the exhaust of a rooftop unit. So it took a couple trips to figure out what the heck was going on because this was a nationals call. The description of the problem was not very good from the building occupant. And finally I figured out, oh wow, like we don't have gas supply going to this rooftop unit because it's just frozen because the exhaust is just dumping onto this regulator and it condenses on the vent port and it just freezes the whole darn thing. And because the building owner doesn't want to pay for anything ever, I cut up a bucket from the back of my van and then just hung it on the regulator so that it would at least, you know, force the exhaust gases to not directly condense on the gas regulator. There's a lot better ways to do this. Maybe just piping it differently to begin with. That would be a really better way to do that. What else we got here? Oh, here's a LiDAR scan of a mechanical room. That's a pretty good idea, I think. Here is a really cool mechanical room. Kind of the center left, we got a set of pumps. There's no redundancy for those pumps. Like each one of those pumps serves a single microturbine. Those microturbines, there's a miniature jet engine in there for combined heat and power. Those things are expensive. One of those microturbines is like $100,000, maybe more. And there's a single pump providing flow to extract the heat from that microturbine. And if it gets too hot, that microturbine has to shut down because otherwise it would break itself. And we had and this was designed with no redundancy on those pumps. Wow, man, a bunch of service calls in that mechanical room to fix that stuff a lot. And of course, once it's installed, the building owner doesn't have money to install another set of pipes or another set of pumps to provide redundancy. And really, like, that would have just been so easy to resolve in the design phase. Here in the upper right of this photo, we got a very large well water expansion tank. One humongous well water expansion tank, no redundancy. So it failed on New Year's Eve. And then I showed up the next day and I piped, because all I could get was that on New Year's Day was 2 small residential expansion tanks that I bought at Home Depot because everything else was closed. And I showed up and piped it in because otherwise this clinic in rural Alaska wouldn't have water to the clinic, which is not an acceptable scenario. And then that huge rubber expansion tank that's on the floor in this photo, it was a 6-week lead time to get. And this is weeks later when I did finally get that big expansion tank. We pulled it out inch by inch, very, very slowly. And man, it would have been really nice to have had 2 well water expansion tanks for redundancy, but whatever. Here's a typical light commercial or residential fuel oil boiler in rural Alaska. I'm trying to remember. I don't remember what I wanted to talk about on that photo. Here's a tangential style air separator. Air separators are really amazing pieces of equipment. They are worth their weight in gold because they help protect the system piping by getting entrained and dissolved oxygen out of the fluid. This is a tangential style, which it creates a little tornado inside there. They really don't work very well. They get the entrained air out, but not the dissolved air. I highly recommend buying the best, most kick-ass, expensive air separator that you can specify, because it is well worth it and will protect so much other equipment. So we replaced that air separator later. We gotta get moving here. Heating. So let's review our themes. Everything breaks, entropy doesn't rest. Let's consider the interface between the fluid and the metal or the piping that we're designing. We need to have redundancy, and what is the maintenance axis? So let's think a little bit about heating. What is the heat exchanger design? Is it a fire tube heat exchanger? Is it a water tube heat exchanger? What is a good fit for that customer? The upper right photo is of a water tube heat exchanger where the flame is blown into the center of that shiny hole, and then the flame squirts out between the water tubes of that heat exchanger. The bottom right photo is a fire tube steam boiler heat exchanger where all those little holes are the fire tube passages for the flame to pass through, and it's surrounded by a water jacket. I'm more of a fan of fire tube heat exchangers because it seems like they're a little bit easier to clean, so it makes my life easier. One of the exceptions to that rule of most water tube heat exchangers are a pain in the butt to clean, except for this European style. It's called a Giannone style water tube heat exchanger, which is shown on the upper right there. For circulation pumps, it's the wet rotor circ pumps are becoming, I think they're pretty great. They seem to be becoming a little more common in larger sizes. They're easy to install. They're easy to replace failed motor heads. But you got to have a magnetic strainer at the inlet because it's a wet rotor. Any sort of ferrous metal really wants to get attracted to the winding, and it will ruin it really fast. If you do have close coupled pumps, it's really helpful if the shaft of the motor is vertical. If the shaft of the motor is horizontal and cantilevered and hanging off of the wall, it promotes the wearing of the pump seal, and which is kind of nice for me because they're easy to replace and I get to charge money for it as an HVAC mechanic. But we could just rotate the pump 90 degrees and just reduce that problem. Redundancy on expansion tanks is a really good idea. Get the best air separator that you can find. Here's an example of a close coupled pump. The top right photo is a close coupled pump that's been installed horizontally. Those seals fail every 2 or 3 years, all the time. In that particular mechanical room, it's kind of like a redheaded stepchild mechanical room, you might say. And then the bottom right photo is a humongous close coupled pump that's about as tall as I am, and it's mounted vertically so that the weight of the motor is balanced on the bearings, and it does less likely to wear out the pump seals. More isolation valves, please. And if you have to use a cabinet unit heater, please install multiple of them in a large entryway for redundancy, because cabinet unit heaters really like breaking. A lot of the stuff we already talked about already. For radiant slab loops, the lengths must be within 5 to 10 feet of each other for the total length of each loop, because the way that they get balanced in the field is in the top right photo, that little blue cap, you just twist that thing to get slow balancing, and it is not precise at all. And it would really help if the linear feet of all of our radiant tubing loops were as close to each other as they possibly could be. And that's softwares like LoopCAD will do that automatically for us. So that's something to think about. 5/8 inch diameter tubing is really nice for glycol, because glycol doesn't flow nearly as well as water. 1/2 inch diameter PEX tubing is acceptable for like indoor or residential use, but glycol really doesn't like getting pushed through 1/2 inch diameter PEX tubing, in my personal experience. That bottom right photo is of a 20 or 22 million BTU steam boiler at a coal-fired power plant in interior Alaska. And before I worked as an HVAC mechanic, I didn't really think about steam at all, because they're not super common. But after working as an HVAC mechanic, I learned that about 1/3 of all the fossil fuels in the U.S. are burned to produce steam. So it's something to get familiar with, something to practice or read about as a designer. That was an intimidating job, but we got through it. Ooh, let's look at some of these photos. These pumps were a nightmare. This was for a laundry facility at one of the local hospitals. Due to lots of reasons, this entire pump skid seemed to fail simultaneously, or one pump failed and then it just never got fixed, and then the second pump failed and never got fixed. So it turned into a real nightmare. And because the laundry for that hospital is critical infrastructure for patient care, this had to be done overnight. So me and 2 other, one plumber, 1 mechanic, we worked in a super hot, cramped mechanical room to try and swap these pumps out, and we failed. And that was that was a brutal experience. And we had to, fortunately, one of these 3 pumps was still operational. So before the morning shift change, we were able to get one of these pumps reinstalled, so that these pumps moved domestic hot water from a huge storage tank across the hallway to the laundry facility. That was hard. That was really hard. Here's me. The access to these pumps was horrible. There was this big control panel directly in front of how we physically got to these pumps. Each pump weighed 200 pounds maybe, and you could barely get your fingers underneath of them. And then directly behind me in this photo, there was a concrete block wall. So, man, if that control panel had been anywhere else, that would have been really nice. So just we were able to do it because we're young, able-bodied guys. But I mean, somebody who was in their 40s or 50s would have really struggled for that. This is one of my favorite mechanical rooms. There's 2 pumps in here. These are split coupled pumps. You can see that they're mounted. The motor shaft is horizontal. These pumps were getting near the end of their useful life. They continued to destroy the rubber coupling between the motor and the pump. So we replaced one of them. Where did that photo go? We replaced one of those pumps preemptively at the start of heating season with a magnetic bearing pump. Here we go. Or with a wet rotor pump. We were really proud of ourselves. Like, oh man, we're getting ahead of the game. We replaced one of these failing pumps with a brand new wet rotor pump. We thought we were kicking butt. And then 2 weeks after we installed that brand new red pump on the left, it attracted some magnetite and weld beads directly to the casing of where the magnetic windings were and just destroyed that brand new pump. And it just so happened to occur on the same week that the older pump failed. So I showed up to this service call at noon on a Friday in late October a year ago, and there was no flow to this building. And it's a very large building, 3 stories. Each story is maybe 40 or 50,000 square feet. I don't know. It's huge. It's not an acceptable scenario for it to lose heat. And I immediately, for the next couple hours, was frantically calling every single vendor in town that I could to try and track down a pump of the correct voltage, phase, and flow to get heat back to this building, because it was going to freeze over the weekend if I didn't. And fortunately, we got really lucky. Oh my gosh, we got so lucky. And we found one of these pumps that was sitting off the books on the shelf of one of our local vendors. And we were able to pipe it in and get it installed before midnight. And the building never got colder than 60 Fahrenheit. That was lucky. Holy cow, we got really lucky there. Here's a photo of how you see those little ball bearings. That's the weld beads and magnetite that are just entrained in the heating glycol moving around the piping. They got attracted to the magnetic field in that wet rotor circulator and just tore it up. That pump is about 4 weeks old, and then it failed and caused an emergency service call that could have gone a lot worse. So we installed magnetic strainers at the inlet of those pumps. This is a base-mounted split-coupled pump with end suction. This takes up a lot of floor space. There's nothing wrong with this. If this had been piped as a vertical shaft configuration, it would have used a similar amount of floor space and had a vertical motor shaft that is perhaps less likely to have a seal fail. All right, we're getting a little short on time. Okay. Let's talk about ventilation for a little bit. We got our themes on the left there that we're going to continue to kick that horse. Nowadays, we have direct drive ECM fans, ECM motors that we can use as direct drive on our fans for just about anything and everything. That is a great idea. There's not really a good reason to use belt-driven fans anymore, in my personal opinion. Maybe I'm totally wrong about that. I'm sure there's some use case scenarios where that's helpful. This top right photo is of a rooftop-mounted exhaust fan that was belt-driven, and it caught fire and failed sometime. And it's just kind of funny to pop the lid off of it and just see it burned up. Fan walls are really great for large air handlers. Because of direct drive fans and ECM motors, it's now a really good idea, I think, to have a fan wall or a fan array in a air handler, because then we have redundancy, and then there's not a single point of failure with a single huge motor and a single huge fan wheel. Also, if one of those fan wheels in the fan array fails, one person can pick it up and move it themselves usually, rather than being this like super lengthy, laborious process that usually has to happen overnight when the building's unoccupied to replace a 700-pound motor or something like that. When we're sizing our air handlers, we really got to make sure that we're filtering or sizing our pressure drop through the air handler for dirty filters, for both the 2-inch replaceable filters and then the 12-inch deep type of filters, because they're usually dirty throughout the life of the air handler. Steam generators for humidification and air handlers, there's almost always just a single steam generator piped, and if you have one of something, you will one day have none of something. So that steam generator is going to break. They have kind of a tough life. So maybe consider having redundancy on the steam generator for humidification. I think it's a good idea to keep HRVs as simple as possible. Heat wheels are really cool. They're super effective. They transfer heat really well, but they break, and there's just more things to break on a heat wheel rather than a static HRV core. Fire dampers and ventilation. This is a life safety item that is easy to forget about. Some jerk has to inspect a fire damper either every 4 years or every 6 years, depending on where they're installed. And they're really hard to get to usually, but this is a life safety item. So as designers, it's probably a really good idea that we try to coordinate that with the other design disciplines. In Revit, it's very possible or easy to show required maintenance clearance coming off of the bottom or side of a fire damper, and then just talk to all the other designers saying, hey, this is a life safety item that has to be accessed. It's required by law to be accessed and inspected. And if we're not coordinating this as designers, it's for sure not going to get coordinated in the field. And then some jerk like me has to crawl around through ductwork and shove their head in tight spaces and have horrible access to check on these fire dampers. And if that's not motivation enough, consider if a fire broke out in one of these buildings and your mother was in a hospital bed on the other side of that wall, and the only thing preventing that fire from killing your mother was that fire damper, you probably would have wanted that fire damper to have been routinely inspected and inspected easily and well. And that's no joke. Like that's what they're for. That they save lives. So we can do a lot better as designers to coordinate fire damper access in our plans. Ventilation. Let's look at some photos there. This is a pretty cool fan that's at one of the local hospitals. It's 200 horsepower motor, 100,000 CFM. This fan is just sitting ready to go. This designer had planned a redundancy for when this motor or fan inevitably fails, and it's on rails, and so that 3 hours after the existing motor or fan fails, you can just wheel the new one to position. So that's pretty cool. Oh, this was a fun job. So this was the motor, a 700-pound motor on a air handler failed, and so somebody had to show up and replace it. It was me and another guy, and so we built a unistrut rack to lift the motor out of position, and very carefully inch by inch wheel it 3 feet out of the air handler door so that we can install the new one. This was, of course, designed and installed before fan arrays were possible. Let's see here. So on the right of this photo, we have a gigantic plenum fan wheel that's taller than I am. That fan wheel weighs a couple 100 pounds. It's to align the pulleys between the motor and the fan wheel is a super critical, like laser alignment type of a job. And this all had to happen after hours. This was at the headquarters of a local bank, and if we think about the analogy of the biological organism, if we didn't have ventilation to this building, that's like telling that biological organism, allowing that biological organism to not breathe, which is not acceptable for the occupants. And that was pretty difficult. That was super hot because there's no ventilation in the building, and we're trapped inside this little air handler cabinet. And it took 12 hours to replace that motor, but we did it. This is not a really relevant photo, but this is an example of the theme that everything breaks. This is a 3-phase contactor that just blew up because it got tired, and we lost ventilation in that building. This is kind of a funny photo. That's a flashlight that's stuck in the fan wheel. Just anything can go wrong. It's just kind of funny. Here's our 12-inch filters. They're super dirty. They're black with dust and soot, and that's how most of these spend their lives. I mean, if you have a really capable HVAC mechanic or maintenance team that really cares, they're going to swap out these 12-inch HEPA filters once a year. But if somebody doesn't care, if they forget, then you're going to have a just plugged filter that's just robbing your pressure drop in your air handler for years and years. So as designers, we need to think about that when we size our fans and motors. That's not, who cares about that? Oh, this is a great picture. This is the venting for a condensing boiler. So on the sides, we got some kind of T's piped in somehow for the outside air coming into the supply direct outside air to the boilers. And then our exhaust, for whatever reason, is piped with a couple 90s so that the exhaust blows straight down so that it can get sucked into the outside air intake. This could have been shown a lot better with just a better detail, or inspection after the installation. That's just kind of a shame. There's no reason for that to get installed that way. Let's make a little more progress. So every summer, the cottonwood trees bloom, and all their seeds, blow through the air and then just get jam-packed on the condensing coils of rooftop air handlers and rooftop condensing units. And on this particular type of rooftop condensing unit, all of the access to the coils are bolted onto the side of the unit. And so what would be really easy to just have a single, hand crank mechanism and to open that door up so it swings out, that doesn't exist. You got to spend an entire day unbolting all these panels just to wipe off the cottonwood seeds off the cooling coils on this condensing unit. So the lesson here is, as designers, if we look at our submittal sheet, how does a human physically access the thing that they need to maintain? So it's really nice if access panels are on hinges, or if they can easily be removed without tools. And like this job could hypothetically take an hour if the access to that coil had hinges on these access panels, but instead it takes a day because you got to remove 1,000 screws. Here's some rooftop mounted air handlers. There's nothing wrong with that, but something to consider is all of the winter and summer operating conditions of any outdoor installed equipment. So what's funny about these particular 3 air handlers on the top of this roof is that the outdoor pressure reference will freeze every time that there's a swing in temperature. So the moisture in the air is inside this outdoor pressure reference tube, and then it freezes, and then the air handler goes down. And then some person just walks up there and blows on it with their breath and thaws it out. It's kind of funny. That's me. The access to these air handlers on this roof is through a roof hatch and a ladder. And there's nothing wrong with that. An able-bodied person will just scurry up that ladder and get on that roof with a 40-pound backpack on their shoulders. Boy, it would be really nice if there were stairs, not a ladder. And then when it snows really heavy, there's 12 inches, 18 inches of snow sitting on top of that hatch, and that is the only access to those air handlers. And then also in the same complex of buildings, there's a rooftop mounted boiler room, and the sole access to that entire boiler room and a bunch of air handlers is through a roof hatch and a ladder that's 24 inches by 24 inches. That is ridiculous. Let's have stairs. What a good idea. All right, let's move on. We're getting close. Air conditioning. Right now, we're just rejecting heat to the outdoors. It'd be kind of cool if we could just be a little more proactive of where we're rejecting heat for any of our cooling operations. Maybe preheat some domestic hot water, or have a domestic hot water storage tank that we can reject our heat to. Just something to think about. We're just kind of wasting a whole bunch of heat by dumping it outside. This is a photo of a large ammonia refrigeration system for a local ice rink here in Anchorage, and there's zero redundancy on the ammonia refrigeration side of this entire plant. And so what you see there is gaseous ammonia just dumping out of a failed weld joint, and somebody's got to show up and fix that, because that ammonia is really expensive, and it's just dumping into the atmosphere, which is not bad for the atmosphere. But if there had been some sort of planned redundancy, 2 condensing units, 2 evaporators, then we can shut things down and repair them without shutting the entire system down and melting a bunch of really expensive rink ice. VRF systems are super cool, and if we remember the trade-off between performance and maintenance, VRF systems are a fantastic example of something that's really cool, high performance, but can become really problematic with maintenance, and it has to be installed perfectly, exactly the way it's designed, and so it requires a very tedious, precise refrigeration mechanic. And I I don't think that VRF is a great thing to try and install in rural Alaska or any place that's outside of Anchorage or Fairbanks. Mini splits are great. Mini splits, single circuit, or even multi circuit, multi-split refrigeration systems are great because they're simple. Every refrigeration mechanic knows how to work on them. They're everywhere, and let's just use more of those. That'd be really cool. This is a really funny photo. So on that ammonia system, at a certain point, we had to valve isolate and vent off the ammonia liquid and gas so that we could make the repair. And ammonia is not harmful to the environment. So this is the preferred means to safely vent off that ammonia, is smoking a cigarette and just pointing it away from yourself. Pretty funny. This is a photo of a rooftop cooling coil. The crane could only drop this 4,000-pound unit off on one corner of the building. And then me and another apprentice moved it Egyptian style a couple hundred feet across the roof membrane. And we struggled for many days to do that. We built up some unistrut brackets so that we could lift it with car jacks to get it off of this super heavy duty custom wood pallet. And you can see that car jack pushing up on that unistrut on the right just didn't work at all. So we built it better, and then inch by inch, we just slowly moved it around. And then, of course, there was natural gas piping in the middle of the roof, so we had to build these little bridges. And man, it would have been great if that natural gas pipe had been routed along the perimeter of the building. So that, I mean, there's lots of rooftop equipment on the top of this roof, and the benefits of the saved pressure drop by having the gas pipe running down the center of the roof line, I mean, versus having that gas pipe on the perimeter of the roof, I mean, it's negligible, completely negligible. But for the lifetime of this building, anytime that rooftop equipment had to get moved or replaced ever, some person had to just, set up a bunch of plywood and drag it across the roof membrane. And it would have been just so much easier to not have that gas pipe there. And of course, there was a 4-inch diameter electrical conduit that had a single Ethernet cable running through it. Good thing we had that 4-inch diameter electrical conduit to protect that tiny little wire, and they were right next to each other. So we had to, build up this ridiculous bridge system, and we were really proud of ourselves. And we made it happen. And that thing weighs 4,000 pounds, and we scooched it across the roof ever so slightly, and we didn't break anything, which was impressive. Here's another really cool job. So this is a rooftop mounted condensing unit that for whatever reason is completely enclosed in this really robust, sturdy penthouse system, but it doesn't have a roof because it's got to reject heat to the atmosphere. And the problem was that there was a roof leak in the roof membrane directly underneath of this condensing unit. And how do we move it? How do we safely lift it and get it out of the way so that the roofers can replace the roof membrane? Well, what we did is we bought a bunch of steel I-beams and then bolted them together and set them up in the best way that we could so that it was supporting the weight of this super heavy condensing unit. I also think that might have been also 4,000 pounds as well. And we had to rig it up in such a way so that it was safe for a bunch of humans to crawl underneath of it and replace the roof membrane and re-level the foam for the roof slope. So we rigged up these chain falls, and then once we got it elevated enough, I don't have a photo of it, but a bunch of high-strength marine-grade rope was tied to the shackles underneath that are connected to the skid on this unit, so that we weren't relied upon a mechanical chain fall to protect human lives when that repair was happening. But why is this penthouse wall thing even there? What's it doing for us? I mean, it's not doing anything architecturally because you can't even see that equipment due to sight lines from the parking lot or anything. It's just in the way, and it was really expensive for somebody to build that, and it's totally in the way. And it's and there's a roof drain inside this little like pit that gets plugged all the time, and then there's no scupper in case that roof drain overflows. And just like maybe we can have better conversations with architects when we see something really ridiculous like this. Here's another photo of another repair on that same ammonia refrigeration system. Fortunately, this one was in summertime and it wasn't 10 below, which made it a lot easier. But we vented the ammonia gas through a bunch of water, so it's less toxic to breathe. And that's a single condensing coil on this huge refrigeration system, no redundancy. So when there's a failure or when there's ammonia leak, the whole system gets shut down, and we're just moving as fast as we can to prevent the rink ice from melting. And the owner is losing many tens of thousands of dollars a day by not being able to rent out their ice rink. If this had been designed with 2 systems sized at 50% of load, then we would have this facility would have continued to have been able to operate without having to shut down and lose all that money. But we got to fix it, because there's no other acceptable option. So this particular repair was the entire header was cut, and then a special custom header was welded up by the factory and shipped up second day air or next day air or something. And then a super duper special welder from the factory showed up to weld many hundreds of those aluminum piping connections. So we had to get all of the ammonia out of this humongous coil and then get it safe to work on. And that was quite the job. Kind of cool. This is the huge ammonia. That's the evaporator coil. Let's forget about that for a moment. Here's a nice example of all the gear required for just a simple, basic refrigeration repair. Of course, the only access to this roof is through a ladder and a roof hatch. So there's a couple 100 pounds of gear that you just have to haul up through the roof hatch just to repair a single piping leak. So stairwell access would be really nice, or maybe locating refrigeration equipment so that it's not on the roof maybe, or like is accessible from an alleyway or something like that. These are things to consider, because is it reasonable for me to ask my grandpa to haul up 200 pounds of gear to repair a single piping leak? Maybe not. I mean, just something to think about. This is the permafrost tunnel up near Fairbanks. This was a super cool job. Some cooling equipment was installed at the entrances to this tunnel, and we did some repairs there. This is like 10,000-year-old permafrost ice. These are just neat photos. This is how they grind out the permafrost ice with this huge auger. That's a really, really old woolly rhino horn. I'm not touching it. Don't get me in trouble for that. This is a mammoth femur, and that's the leg bone of a Pleistocene horse or something like that. That was a really cool job. And I got to enjoy being alone in these super dark, cold permafrost tunnels. That was just really neat. The ammonia thing failed again. That was great. This is a mini split system, multi-zone ductless mini split refrigeration system installed in Nikolai. I felt comfortable installing this in Nikolai because these systems are so simple and robust and reliable. There are 2 flights in and out of Nikolai a week, and it is really difficult to make repairs there in a timely way. But this is an example of my confidence in simple, robust refrigeration systems. This is also an example of a place to definitely not put a VRF system. We'll just move past that. These rooftop condensing units are horrible for lots of reasons. The condensing coil is hidden behind all of this gear, and then the airflow from this photo is from right to left. So all of the cottonwood seeds and dust and dirt that's in the air in the summertime has to get blown past all of that, all those multiple compressors and gear, and get stuck against the suction side of the cooling coil, and then you can't clean it out. Every other single piece of rooftop mounted or any sort of condensing equipment, the cooling coil is located in such a way so that as the air is drawn through the coil, all the seeds and dust get stuck on the outside, and then any person can just walk up and brush it off, except these ones, because whoever designed these at the factory was a jerk, and they just didn't think about that. And it like literally impossible to work on, like so incredibly difficult to work on. Just to make a single repair on this refrigeration system took 2 guys 4 days, which was just dumb. The blowers or the fan wheels on these condensing units are squirrel cage blowers, whereas every other single condensing unit in the world is a propeller type fan with that's where the motor is directly mounted onto the fan wheel. So this is a huge blower that takes up a lot of floor space, and is also has a belt on it that has to get replaced when the belt inevitably fails. So this is an example of, as designers, let's look at our submittal. How is a person going to interact with maintaining this equipment? This is a wonderful example of one of the worst maintainable pieces of equipment that I've ever touched. Oh, I thought I had more photos of it. Oh, and of course, the evaporator systems on the inside of the building for the same manufacturer are similar. The way that it was designed to be hung from a ceiling, the anchor points to support this piece of equipment forced it so that the unit strut are directly in front of the maintenance doors or the access doors to get into the controls cabinet. So it's impossible to work on. It's ridiculous. Yeah, real good. All right, we're getting a little short on time here, like we're out of time. Let's talk briefly about mechanical room layout. The equipment in this mechanical room is fantastic. It's really good gear, but everything fails. So those pumps are going to fail one day, and there's really horrible access to get to them because the piping between these 2 boilers is extremely tight, and I'm going to have to stand on top of those delicate thermometers to replace those pumps. So everything fails. Every piece of mechanical equipment will break. So how is the maintenance guy going to be able to get his hands on it? This is an example. This is a really old boiler room where things are so old that they're breaking. This is a good example of wonderful maintenance access. You can walk around pretty much every single piece of equipment here. It's really easy to replace those 40-year-old pumps that are on the right of that photo. Really easy to get to the boiler on the front of that cast iron boiler. Lots of nice floor space in this mechanical room just to stage your tools and everything. Here is some photos of replacing some large diameter steam valves in a local hospital. And this is the type of conditions that there's a steam pressure reducing station above this mess of piping. And that was maybe not a great place for that to get piped into, but we made it happen. Maybe that steam pressure reducing station could have been located so that it was on the wall, not in the ceiling, hidden behind a whole bunch of high pressure, high temperature steam pipes. So the heat and domestic hot water production for this hospital was shut down on a weekend, and then we kicked butt and made it happen. That's a good picture, Joe. Here's another example of access to a rooftop mechanical equipment. There's this wonderful stairwell that's 4 feet wide all the way up, except for the last couple steps up to the roof. The stairwell is suddenly 20 inches wide and is like a ship's ladder stairwell, and it's unnecessary, completely unnecessary. So it required a custom order for this last few steps of the stairwell, and it's really difficult to carry any sort of tools up there other than just what you have in your pockets. So this is an example of us communicating with the architects of, hey, how's a regular person going to be able to access the rooftop equipment? Okay, let's forget about that. Okay, let's talk briefly about self-care, and then we'll head out. So self-care is super important for all of us as designers. Due to deadlines, we're under pressure a lot to work late, and we need to be really careful about not pushing ourselves or our physical bodies too hard. Sleep is required for us to survive, and it's just something to consider. So lessons learned as an HVAC mechanic is that a big one that I was forced to learn was if we have to take care of ourselves first so that we can better serve others. So if I'm supposed to be the guy who shows up no matter what the weather is to fix the gnarly problems that other people have failed to solve, then if that's happened to me on a daily basis or hour by hour, then I need to be really on top of my self-care. So all of the bad habits that I learned working as an office design engineer of working late and not eating high quality food, those lessons just piled on top of me really quickly working as an HVAC mechanic, and I had to learn really fast to improve those things. You will, at some point in all of our lives, we will find ourselves in a bad situation, probably due to some of our own bad decisions. And it's really important to not allow ourselves to just dwell on that. And because a lot of times there's nobody else who's going to help us better than we can help ourselves. So if you're in a bad situation, just don't stop. Don't hang out there. You got to make forward progress. And there's like so many dozens of times where I've been alone late at night in a dark, dirty, loud mechanical room, not knowing how to solve this problem, and just kind of realizing like, well, I don't want to sleep here tonight, so I guess I might as well try something new and try to make progress in some other area. And we always have allies out there. There's always somebody who is going to pick up the phone and be willing to talk with us about whatever our work problem is or whatever problem that we're facing in life. So we're never alone. And that's, I think, is a really important lesson that we need to continue to remember. So a review of what we talked about. So the wheel of ignorance, it's really important to be empathetic for other people's perspective, I think. We talked about the lessons learned in the trades, the engineering versus trades perspective. We talked about our ongoing themes, that everything breaks. Rust, chaos, and decay don't stop for anybody. We got to be cognizant of the physical interaction of the materials and fluids that we're designing with. You got to have redundancy because it's going to break. You got to have maintenance access because when it breaks, some human being has to show up and put their body, in sometimes harm's way to fix the thing. We talked about equipment specifics with all of those photos. We talked briefly about measuring layout and, of course, some important self-care. Thanks so much for your time. I want to thank Craig Fredine and Elena Hartford for letting me be here. I want to thank the United Association Local 367 for training me, because sometimes it's hard to fill the glass that thinks it's already full. And I'm really thankful for Cool Air Mechanical for letting me stick around and continue to train me. And of course, where would any of us be without our friends and family? If you want to get a hold of me, here's my contact information. I answer that phone number 24/7. So if you ever have any questions or concerns or would like the perspective of someone who sees both worlds, please give me a call or shoot me an email. Thanks for sticking out this long. And that's the end of the presentation. Come on, any questions? Cool, thanks. Oh man, I don't know. All right, is that it? Leave? All right, thanks for sticking it out, guys.